And that constant part, which is blowing up, gets multiplied by 1 minus beta, so it doesn't blow up, and it ends up over here. Gives you the eta star. Yeah. I'll write that down over here. So that's the ugly way to do this. you look at a representation of this value function as a constant, plus something like this, and then you basically show that the tilde part ends up solving this equation. That's the ugly part. The beautiful way is to represent this as a linear program, find the dual of that linear program, and that it turns out to be equivalent to the dual. It's really amazing. So H star turns out to be a sensitivity to the dynamics constraints. It's really something. Actually, it's not that true. Hold on a second. Jumping a little bit ahead, that's called the Q function in Q learning, and that is a dual, the optimal dual function in the dual of Mann's linear program, and that's the sensitivity to dynamic constraints. Yeah, that's what it is. Yeah.
So just clarification.
Yeah.
So the H star in the Q function over there, that's the H tilde and other?
No, I'm saying that there's two ways to come across the average cost optimality equation. One is through duality, which I'm not, in previous times I've taught this course I've gotten into, but I don't think there's time this time. But the typical way you'd see this in a course is doing just what we did in the homework. Is you basically, once you minimize, you get a linear equation just like you analyzed in the homework, and the solution then can be written as something that's bounded in beta plus a constant. And so now I let beta go to 1, and I find this actually converges to something, and this doesn't. But when you plug it all in and fool around, you end up multiplying by 1 minus beta, And so the pi beta of C converges to the pi for the limiting model, and that gives you the optimal thing, yeah.
How can we use that trick for the discounting case to apply to the average cost? I don't see that.
Well,
because that involves the beta of C.
No, I just told you right here. So I take this. I'm not going to do it today. Good idea. We'll do it in homework next homework. I'm saying if you plug this in here. No, in fact, you did do it in the homework.
We did it for discounted, but not the average.
No, you look at the limit. In the homework, I asked you to say, what's the limit as beta goes to 1? Right. And it's a solution to the Poisson equation, yeah. And it works. I'm saying that what you did in the homework carries over to the controlled setting.
For the discounting?
No. In the homework, I asked you to decompose the discounted cost as a sum of something that's bounded in beta plus a constant over 1 minus beta. So you did that. And then I asked you in the homework, what does this converge to as beta goes to 1? It converges to a solution of the Poisson's equation.
Yes, but that Poisson equation was for the discounted case.
No, it's a Poisson. There's only one Poisson equation. There's no discounting. When beta goes to 1, it's all. No, I don't want to review the homework now. The homework you did. Look at my solutions if you didn't do it. The theorem was that as beta goes to 1, H tilde beta converges the solution of Poisson's equation. The Poisson's equation never has discounting. Okay? And so that homework, the reason I gave the homework is that it carries over to this case. Okay? So that's one way to do it. But there's another way to see this that comes out. There's a third way, and it's through this thing here. Under conditions again. Under conditions, you can also do this. And here's, oh, by the way, again, this is not unique because I can always add a constant to both sides and get another solution. Okay, so while these other value functions were unique, this is not. All right, but one solution is given by a shortest path problem. All right. So I'm not saying it's obvious, although you can actually derive this from this. You can go through and sort of iterate this equation, and maybe I'll do that later on. I just don't want to do a lot of theory now. I want to give you the big picture first. But you can iterate this equation just like we did without the minimum, and obtain that under some conditions. You know, just like, you know, one can represent Poisson's equation like that without the minimum. You can get from there to there under some conditions. And you can also go back, and we know, I told you that the shortest path problem solves a DP equation, all right? But it looks like a mismatch. Because remember I had that indicator function of S complement. You know, here S is just equal to this point X bullet. Sorry if that's hard to read. I'm looking at from K equals 0 up until just before, you know, the first time I return to the state X bullet. So we know the shortest path problem says this is equal to the minimum over U of C of XU plus the sum over Y not in S, which means not equal to X bullet. And with a tilde, sorry. So why the mismatch? So here I've got a very nice equation, 8 star plus blah, blah, blah equals that plus that. And there I've got something different. What's going on? There's a contradiction. How do I fix it? Keck's theorem. It turns out that Keck's theorem generalizes as well. And so basically, if I plug in X bullet, I'll get 0. So I'm stating a bunch of facts, you know, I'm changing my style. I'm feeding you facts, and the facts that are suggested by the theory for Markov chains we had before. Okay, and yeah, and you know, proving that, yeah, this is deep. From going from that to knowing that's 0 is deep. So, you know, forget that. Just say that from this, you can get that. And then I can always assume without less of generality. Well, actually, put it this way. Any solution, I would just get plus h of x dot. So you can prove that. You know, basically that last term is the h of x dot. You know? So if you gave me any solution to this, I could represent it as this minimization plus this term. You know, and that's generalizing what we did before. Okay, go back and look at your notes. All I'm doing is saying everything we did for uncontrolled Markov chains has a generalization of controlled Markov chains. And if you really want the math, it's in those chapters, in that one chapter, chapter 9. But I just don't think, we don't want to spend 6 weeks on this, so I'm not going to cover it. All right? Okay, yeah? Is that okay? I mean, it's up to you all. It's just a matter of trying to have time allocation, you know? Yep.
What is actually average cost?
It's nothing. That's the trouble. You know, it's like the most intuitive. I mean, this is one thing that gives you some intuition, that it's a solution to a shortest path problem. You know, because constants don't matter, but for the relative cost, you know, the cost minus its the optimal value. That's not very satisfying, you know.
It's not average.
It's nothing. H is just nothing, but except in this beautiful theory. So this Q function is the dual for the sensitivity of some invariance constraint. It's absolutely awesome. And again, you can find that in chapter 9 of my book. I won't cover it. It's all too much.
What was the question again?
Oh, what is H? What the hell is it? And I'm saying either you could see it from this again. I mean, that's it. So it's the limit of the tilde part of the discounted case. So that's a little satisfying. You know, or it's this monster here, or it's a sensitivity. It's a and that is really awesome, by the way. It makes me so sad I can't cover it. This stuff here. I wish we had time. I wish this course had 2 parts to it. Okay. So what have I left out? I left out something huge, I realize. What did I leave out? So once you solve this thing, what then? Our goal is not to get this, right? Who gives a damn about 8 star? What's our goal? We want the policy. I forgot to tell you what the policy is. So you all know what the policy is, right? If you don't. So remember how all these DP equations were formulated. We were minimizing over all sequences U0, U1, U2, U3, and so forth, right? Well, when we did that, remember there was a U0 in there all along. And that U there is U0. So I forgot to say we get state feedback. You know, so U star, the optimal policy at time k is some deterministic state feedback, because the solution to this thing holds under such general conditions it's ridiculous. So there's no randomization needed. We'll need that for other things. And phi star is just the argmin. I mean, it's the same for every case. All right. Cool. So we should take a break, but just one more comment, okay? Unless there's a question. Yeah.
So can we figure out eta star from the Lyapunov analysis?
The only way to get eta star is to compute this monster. You know, it's horrible. You know, that's the tragedy of this area, is that these fixed point equations are nasty to try to solve, you know. I mean, it is a linear program, so everything's convex and nice, you know. Solving this problem as it stands doesn't look like a convex problem. It looks like an awful root finding problem. But because it's all based on a linear program, it's a wonderful convex problem. And that's really useful, by the way, for approximating optimal policies, this is really useful because you can approximate this linear program. So I will tell you what this linear program is. We will mention that. But then, yeah, I mean, forget it. I mean, find the 8 star, you know, I mean, that's why we have reinforcement learning today and all sorts of approximate methods. Because it's just, it's a, I mean.
And this
Yeah.
whole thing,
Yeah.
I mean, maybe you
Go on.
understand my question.
Oh, no, I guess I didn't.
I was saying, like, I guess I don't know what we can still formulate the Lyapunov function for all this, right? This is
I know what
current
you
stuff.
mean. I mean,
We did it for the uncontrolled markup.
oh, well, sure. If somebody gives me a policy, I'm going to evaluate its performance for the Lyapunov function. Absolutely.
Okay.
Yeah. Oh, absolutely. Okay. Yeah, sure.
And then,
And that's related to the point I'm about to make. Yeah.
okay.
Yeah.
Second question would be, like, this works for model free and with a model too, right?
I don't know what you mean by that.
So,
Yeah. No, I have no idea. You know, I mean, I've got a model. Yeah, there's a model. Yeah. No, none of this. No. That conversation's for another planet. Maybe when we get to RL, we can talk about that. No, we got a model. We've got a model.
is the
That's the model right there. We have it. Yeah, we know it. We have it, and we'll get to not knowing it later. That's it. You're thinking about, you know, after Mardi Gras. Yeah.
After when?
Mardi Gras.
Mardi Gras.
Yeah. Okay. So there's a concept called inverse dynamic programming.
So here,
Yeah.
value iteration makes sense, right?
Yeah. Oh yeah.
More
But-
so than the previous.
Nah.
I mean, I know what you're saying, but
No, I mean, I still think, I mean, the thing is, the reason you use successive approximation, which is value iteration, to solve this equation. It's the most standard way possible. And it's so slow, you can't believe it. And you do it because it's lazy. I mean, look how easy it is to code. Well, we haven't defined value iteration yet, but I will. And it's so trivial to code, it's ridiculous. You know, if you really cared, you would do something smarter. You know, something in between value iteration and policy iteration, which we'll talk about. Yeah. All right. So, another thing I forgot to say is that this is called a relative value function. You know, they had to come up with a new name for it because it's such an abstract thing, you know. The thing is, it's sort of obvious, you know, because give me a C, you know. Give me an eta. And I'm going to look at what's called the Bellman error. So it's going to be the error in this minimization. And I'm not sure which direction you use to write it. Is this minus this or this minus this? What's our typical direction? I don't know. There's no standard thing, but anyway, let's write it like this. It's the it's minus h of x plus the minimum of a u of c of x u, minus eta plus pu h of x. So I'm taking this minus this. I might change my mind later on. All right. So h is just a function. You said h is x squared. What doesn't make sense? X takes on values a, b, c, d. But I mean, just h is any function. All right. And c is any function. Maybe it's a function I really care about. but h is just arbitrary. And I can always define this, which is the Bellman error. And then I can rewrite this in a different way. I can write this as h of x equals the minimum over u of c of xu minus eta plus pu h of x, right? Or maybe not? You're supposed to look at me funny. That's this, isn't it? So I cheated. How do I correct this? That doesn't imply that. How do I make this imply that? Yeah, I'll put a little check mark there. And so basically I subtract it, you know. So c check of x u is just c of xu minus the Bellman error. All right. Now this is a beautiful machine, because what you do is you go through and you find some function h, like our fluid value function ideas, these ODE tricks. You come up with some funky function, and then you go through and there's a cost function you really do care about, right? And then you choose eta to make the Bellman error as small as possible. And then basically, if this is small, if b is small, then you've optimized a cost function that's just a bit different than what your manager gave you. Who cares? Cost functions are artificial anyway. So eta is the optimal cost. For C check. And again, we want to choose, you know, of course, beta. If I change eta, I change beta. It's just so basically, I would like to center beta b to be as small as possible, or something. You know, you just move it around so it's enormous small. And so if b is small, then we're approximately optimal. I mean, and you can really quantify this. So basically, this minimization gives you a policy, which I'll call phi h, right? And if B is 5% of C everywhere, then I'm 5% within optimal. I mean, it's just it's very, again, that should be a homework problem as well. I'll keep track of this. It's very easy to see that. So basically, you want if B is small relative to the cost, then you've nailed it. Yeah. Okay, so we're going to use this in the next hour. So I'll give an example. I'll see how far we can go. All right. But we'll break for a bit. Okay. Yeah.
I mean, like, yeah, as you mentioned, you do need access to P, but if you don't have access to P, then you can use Monte Carlo techniques or something.
Well, that's the third of the course.